Right, this is our lesson on modern atomic theory and quantum numbers. This is an introduction to the quantum mechanical model of the atom, which is our current model of the atom. So if you remember back when we started learning about the atom, we learned about Dalton's model, and then we moved into Thomson's and Rutherford's and Bohr's model of the atom. So the quantum mechanical model is our current model of the atom. The nucleus is going to stay the same. What we're going to learn about is how the arrangement of the electrons changes from Bohr's model to this new modern model of the atom. So we'll review. Remember, the atom has a small, dense, positively charged nucleus. So we can fill that in, surrounded by electrons that travel in a wave-like motion. Okay, so depending on the energy of that wave or how big or small the wave is will determine, what energy level it's in and what sublevel, which we'll learn about as well. So it is impossible to know both the location of an electron at any particular time as well as the direction that it is traveling. They're moving in a wave-like pattern constantly, really fast. So you can't know both its location and the direction that it's traveling at any particular point in time. This is called the Heisenberg uncertainty principle. I would suggest with this part of the unit making some note cards of these new kind of rules that we're learning. There will be a handful of those, about 4 of them, that you're going to be learning. So maybe make a little note card or write these down as we go through them. Okay, so back here to our modern model. So since we can't know exactly where they are, the direction they're traveling in, we can determine the general area or space that the electron might be found in. It's kind of like an address. So kind of like we know that, we live in the US. Now if we want to get more specific, we're in Ohio, then we're in Carroll, Ohio, and then maybe, I don't know, maybe that you live on Market Street. And then maybe we can get, some kind of address from that where your house is. So just like we can do an address for your location by going, from most general to most specific, we can do the same thing with an electron. So the most general part of the address for an electron is the principal energy level. This is energy levels 1. These correspond to energy levels 1 through 7, which if I click over here, correspond to the periods on the periodic table. So we have like period 1, period 2, period 3, 4, 5, 6, 7. So those correspond to the principal energy levels. Okay. Sublevel, SP, D, and F. We colored those in on our periodic table. So you'll want to get out your periodic table and look at the back of it to the parts that we colored in with the SP, D, and F sublevels. Then we can get more specific as to exactly what orbital the electrons are in. Each orbital can hold up to 2 electrons. Now, electrons have the same charge, so they don't like hanging out together in the same orbital. It's almost like they're too much alike. So if they have to share a room or an orbital, they're going to have opposite spins. So any 2 electrons can share an orbital, but they're going to spin in opposite directions. Okay. So from most general to most specific, we go principal energy level, sublevel, orbital, and then spin. And just like if I was standing outside your house, I would not be able to tell exactly which room you are in and what room you are moving to at any particular time. So that gives you kind of a picture of what these electrons look like in our current or most modern model of the atom. So a quantum is the energy that the energy of an electron. And this is based on its location. How far away from the nucleus it is, what sublevel it's in, what orbital it's in. Okay? And it takes a certain amount of energy to get those electrons to move to other energy levels. And that's what a quantum is. It's that set amount of energy. So quantum numbers, the principal energy level, sublevel, spin, and orbital, I skipped that one, are like the address of an electron. Okay, they describe the most likely location of that electron. So just like I could say, okay, typically I would find you at your house. Okay, but I don't know exactly what room in the house you are in. All right, so the four quantum numbers get, they do have symbols that go with them, N, L, M, and S. The principal energy level is N, and we saw this in our electron, energy, and light activity where we had to say what energy levels electrons were transitioning between. So we have N equals 1, we could label this as N equals 2, N equals 3, N equals 4. Okay, so electrons can transition between those, or they can just be sitting here in their ground state energy levels. Okay, so it shows the distance the electron is from the nucleus. So an electron in energy level 4 has more energy than an electron in energy level 1 because it is farther away from the nucleus. Okay. Again, the energy levels correspond with what period the element is found in, and the number of electrons each energy level can hold varies. So the first energy level holds 2, second holds 8, then it goes to 18. Then 4 and 5 has the most at 32, then it drops back down. You do not need to memorize these, as we will learn how to use our periodic table to determine the number of electrons that an energy level can hold. But you probably remember from drawing Bohr models that you would draw like 2 dots on the first energy level, so that's 2 electrons. Then you would draw your second, you could hold up to 8, third could hold up to 18, and that's probably where you stopped. So in this unit, we're going to find out why we see these numbers in each of the energy levels. Okay. All right, so let's move down here to sublevels. So we have energy level, now we have sublevels. An electron can travel in 4 different shapes around the nucleus. So if you scroll down a little bit, you can see the different shapes. The S sublevel has electrons traveling in a sphere shape. So they're traveling in a wave-like pattern within the sphere. Keep in mind that atoms are 3-dimensional. They are not 1-dimensional like we see on paper. The P sublevel is a dumbbell shape or a propeller if you choose. D has a flower shape. And F is a complex flower. So each of these have unique shapes. These you need to memorize. Okay, you have to know the shapes of the sublevels. Okay. The magnetic number, these tell you the number of, this tells you the number of orbitals or the orientations that each shape can have around the nucleus of the atom. So this gives us the number of orbitals. So I'm going to scroll down here so we can see these different shapes. So an S sublevel has only one orientation that can be in. Like you can only rotate a sphere one way around the nucleus of an atom. So this will hold up to 2 electrons. So you can imagine 2 electrons traveling around in a, in a wave-like pattern within that sphere. The P sublevel is the dumbbell shape, and it has 3 different orientations. So there are 3 orbitals in the P sublevel, 1 orbital in the S sublevel. The D has 5 different orientations, so that is 5 orbitals. And then the F has 7 orbitals. It's very complex, okay? Because there's 7 different orientations that these electrons can be found in the F sublevel, okay? We go back up here. Sorry, I'm going to scroll down a little bit. So as far as spin, so within the orbitals. So now if each orbital orientation, or just orbital, can hold a maximum of 2 electrons. If 2 electrons have to share an orbital, or they don't like to share, they will spin in opposite directions. Okay, so since they spin in opposite directions, one will have an up spin, which means the opposite, we notate that by a down spin. Okay. Let's look back up here at our orbitals. All right. So if there's 1 orbital in the S sublevel and each orbital can hold 2 electrons, the S sublevel has a maximum of 2 electrons that it can hold. The p sublevel has 3 orbitals times 2 electrons, tells us the p sublevel can only hold 6 electrons. The d sublevel has 5 orbitals times 2, gives us a total of 10 electrons. And then when we look at the F sublevel, there are 7 orbitals, which means that we can have a maximum of 14 electrons, so 7 times 2. I want you guys to pull out your periodic table and see how that corresponds. So if you remember, if you look at your periodic table, and there's a little tiny one down here, the S sublevel that we have colored in has 2 groups. There are 2 electrons that the S sublevel can hold. If you count the number of groups in the P that we have colored in, there are 1, 2, 3, 4, 5, 6 groups colored in the P sublevel. That equates to the 6 electrons that the P can hold. If you don't believe me, we can do the D sublevel. Count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That equates to the 10 electrons in the D sublevel. And then try it with your F block. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 columns, or kind of like groups, in the F block that we have colored in. That corresponds perfectly with what we have learned about the arrangement of electrons in an atom in modern atomic theory. Okay. All right, so we're going to summarize down here. All right, so we're going to summarize what we just went over. Let me get a pen here. So we have sublevels S, P, D, and F that are found within the energy levels. Shapes for an S, that is a sphere. P is a dumbbell. D is a flower. And F is we'll just call that a complex flower. Okay. So orientations around the nucleus. What we're really counting is the number of orbitals. Okay. So we would say 1 for an S, 3 for a P, 5 for a D, F is 7. Then to get the number of electrons, because each orbital holds 2 electrons, just multiply that by 2. So we get 2 electrons, 6, 10, and 14, which corresponds to the number of groups that we have colored in on our periodic table for each sublevel block. So can more than one electron have the same quantum numbers to describe them? And we need to be able to explain. So let's go through each quantum number. The first quantum number is N. N is the sublevel. Can more than one electron be in the same sublevel? And the answer to that would be yes. If we look at the periodic table, we have elements that are found within the same period. So this whole second period with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all of their electrons would be found in the second energy level. Also, you can see lithium would have 1 electron in the second energy level, but beryllium would have 2. Boron would have 3, carbon would have 4, 5, 6, 7, and 8. So yes, more than 1 electron can share an energy level. So I'm going to check mark there. The next quantum number is L. L is the sublevel. Can more than 1 electron be at a sublevel? The answer to that is yes, because as we found out, the S sublevel holds 2, P is 6, D is 10, F is 14. So more than 1 electron can share the same sublevel. Can more than 1 electron share the same orbital? Answer to that is yes, because each orbital has 2 electrons. Now, what if there are 2 electrons in the same orbital? Okay, so for the quantum number S, this is the one that makes it so that no 2 electrons can have the same 4 quantum numbers, describe them, because if 2 electrons are in an orbital, one is going to have an upspin. Oh, that says orbital. Sorry. One electron will have an upspin. The other electron will give a downspin, which makes them have 2 different quantum numbers for S. So N could be the same, L could be the same, M could even be the same. But if there are 2 electrons in the same orbital, then their spins are going to be different, which would give them different quantum numbers, right? So the practice for our little introduction here to quantum theory, to the quantum model of the atom, is on the next page. So you can complete this and either show me when you return or take a picture and upload it to this assignment in Google Classroom.